Today I'll be looking at graphing this piecewise defined function. A lot comes down to just your knowledge of graphs when you're trying to graph a piecewise defined function. So we have this criteria where we want -6 for x equal to only 2, and then x squared minus 2 for x not equal to 2. So that just indicates we want the graph of x squared minus 2 everywhere but 2. And then we want the graph of -6 the only spot at at positive 2. So what does -6 look like, first of all? -6 is just a horizontal line. So if we didn't have any sort of restrictions, the graph of -6 would just look like this. It'd just be a horizontal line at -6. But since we do have the restrictions of we only want this graph for when x is equal to 2, what that means is that when x is equal to 2, which is right here, we only want -6, so it's just going to be a point. Just like that. That's it. So only when x is equal to exactly 2 do we want this graph of -6, so it's just a singular point. Now, for the other part, we want x squared minus 2 for x not equal to 2. So everywhere else but 2. And x squared minus 2 is, just the knowledge of x squared, is a parabola. Looks like this. And we're going to get some defined points. But then x squared minus 2 is just shifted down 2 units. So x squared would be right here. And I'm going to erase this, but just kind of showing you. And then x squared minus 2 would be shifted down. So it would look something like this. So what we want to do is we want to get definite ordered pairs, and then we want to keep this in mind that we want everywhere but equal to 2. So let's go ahead and do that. So I'm going to grab a couple ordered pairs like f of 0, f of 1, and then we don't want 2. So I'm going to go around 2, so let's get f of 3, and then we'll see what we do there. But we understand what x squared looks like. It's just a parabola, but we want it for everywhere but 2. But if you want to get definite points and an exact idea of what this graph is going to look like, you can just take some points. So we're going to plug in 0. 0 squared minus 2 is -2. So when f is equal to 0, we get -2. So it's going to be an ordered pair there. F of 1, 1 squared minus 2. 1 squared minus 2 is -1. So for when x is equal to 1, we get a y value of -1. Then we don't want 2. And then on the other side of 2, f is equal to 3, that's going to be 3 squared minus 2. 3 squared is 9 minus 2, which is 7. So when x is equal to 3, we're going to get the y value of 7. Let's just get f of -1 and maybe f of -2 just to get an idea exactly what's happening here. So -1 squared is +1. Positive 1 minus 2 is -1. So when x is equal to -1, we get -1 right here. And then -2. So that's going to be -2 squared, which is +4, minus 2, which is 2. So -2, 2. So over here, it's going to do something like this. And then here's what we have to be careful with. X is not equal to 2. So we want all the x values not equal to 2. So it would be, here's a little way that you can do this. Let's get f of 2. F of 2 is 2 squared minus 2, which is 0. So at the x value of 2, we're going to be at 0. So here's what I'm going to do. I'm going to go up to that, and I'm going to put a hole at 2 like that, and then that's going to indicate that we're going to go like this. So that just means that here's the graph of x squared minus 2, not existing though at 2, where when x is equal to 2, we have this point that was -6. So that's usually a nice way of graphing the piecewise defined functions, is just getting an idea of what's happening at that restriction point. So then you could put a hole there. So that means that we're not actually going through that point. It's going up to that point and then going on the other side of that. So hopefully that helps with graphing this piecewise defined function.